Shafting. Very important. You got to do it right or you know you're going to get it. Number one thing in shafting. Loading. Make sure you don't break it. How did you mount it? How do you attach things to it? Shafting includes smooth shafts, like for a bearing rail. Shafting includes the shaft of the lead screw itself, but this is actually a roller screw. So basically, shaft is generally something round. It can be octagonal. It can be square. Usually round because it fits through some sort of rotary motion bearing or linear motion bearing. Shafts are loaded in various ways: axially, torsionally, or bending. Those are the three components. Shafts normally have different diameters along their length according to different functions that are there to be performing. And it's the transition between diameters or the inclusion of features like a hole for a pin or a keyway that may seem very simple but can lead to very high stress concentrations. And remember, to design machines, you should have a good class in stress analysis, mechanics, theory of elasticity, understanding how when you apply stresses to things, they cause things to break. But very importantly, being able to visualize, I'm putting stress into something and the stress is flowing in the object and it hits a hole. It's got to stop and go around the hole, and that's uncomfortable. That leads to stress concentrations. This is the finite element analysis output. Here are some stress concentration factors you can write right into a spreadsheet that will allow you to do very rapid design comparisons without having to run and get a proper meshing to do the finite element analysis, because not all finite element analysis programs will be able to handle the transition from a large structure to a very, very fine structure and give you fine enough meshing to give you good results. In general, the key is smooth transmission. Avoid harsh changes. Even in things like keyways. It may seem simple to make a keyway in a shaft. Cutting it out with a milling cutter. You may think that's very fine, and in most cases it is. But this sharp edges on the end here the sharp edges here and the sharp edge transition here, well, it can lead to very high stress concentrations. You most typically like to use gentle, rounded, although it's very rarely you ever see anybody do a rounded key because it's more expensive. But if you really want to do things, the ultimate and minimum shaft diameter, maximum torque, you wouldn't use a key anyway. But if you were, you would round that, and back at the end, this should also be very gradual. This is called spooning of the keyway. Okay? There are other shapes for transmitting torque with shafts: splines, trilobes. There's a lot of work that's been done over the years to get to shapes that are maximally good at transmitting torque while minimally disruptive in terms of causing stress concentrations. And it's not just that you're transmitting torque with a shaft. Remember, your shaft is typically loaded such that it's taking the weight, for example, of a wheel. And if you have a keyway where it's taking the load from the wheel, that can cause bending and stress in the keyway. So ask yourself this question. If you have a shaft coming out of the motor, here's your motor gearbox, and we'll give it a little more length here, and you happen to do this with a hub and here's your keyway. Compare that design to a design that, what would you do? I don't see anything wrong with that. That looks perfectly fine. I see that all over the place. What's he talking about? Blah, blah, blah. Everything you see, you always want to say, gee, I think that I feel comfortable as it is. Hey, dude, let's turn it over and see what happens, baby. Maybe it's even better. All right. I don't know what's going to happen, but let's see. Shaft. And the function of the hub is so I can have a little set screw that pushes on a keyway, a key, to transmit the torque. The function of this part of the shaft is to bear the load. Here's the bearings in the shaft. Bearings in the shaft. Notice here the function of the shaft to bear the load, smooth path through the structural loop, no stress concentrating keyway features in it back here. The torque is transmitted through the shaft, then comes up through the keyway to be transmitted through the hub to twist whether this is a wheel or a gear. So I've separated the design parts of the shaft that transmit the bending load from the wheel and the torsional load to the keyway. Back here they're reversed and they're mixed up, and the torsional load is coming through the shaft while it's being bent, and you get a more complex stress state to cause failure in the shaft. Very subtle difference. So when you look at a motor output, the hub, you'll usually will see the keyway does not go all the way back, and it shouldn't. And if you're buying the motor, you should tell them you don't want it that way. This will give you a very robust design. So the moral of the story is it's not just that, oh look, I have sophisticated analysis tools. I can run finite elements. I can do the element design on this and show, okay, I have stresses. Thank you. It's, dude, how do I do a design so I ain't going to have stresses in the first place? Because you may do the analysis here and say, oh, bummer, it's going to fail. All right, make it bigger, more powerful. Costs money. Okay? How do you minimize cost, maximize quality and robustness? Mounting of the shafts. It's not just that you're going to load the shaft by external loads. When you mount the shaft, let's say this is a linear motion system. Oh, that's wonderful. It slides so nice. Oh, that's really good. Oh, yeah. But if it was misaligned because you design the machine and then loads are applied to the machine, right? And everything has a finite stiffness. I loaded the machine, that's when I tighten this screw here and it bend this a little bit, and this plate looks really strong, but it's misaligned a little bit. Hey, look what happened. What were nice bearings are now, ow, so that doesn't matter, I'll put a bigger motor on, I'll force it, yeah. They ain't gonna work so long. The bearings that support the shaft are misaligned. Add another bearing in the middle. Use the shaft to keep the bottom from bending. No. Okay? So be careful of how many bearings, misalignment of bearings, and you can calculate all this. It's based on clearances and the very simple geometry of, you can write your own spreadsheet for this. I bet there's even one that exists in the collection. The shaft will have some shape because nothing's perfect. How much clearance between the bearings and the shaft is needed such that I do not over-constrain the shaft? Will the shaft, when it bends, cause stress risers on the bearings, where I had calculated the size and strength of my bearings, assuming that I had even pressure across the bearing. Well, it start to wear here and here. 1 over ouch equals ah. Maybe then the bearings have to be in a spherical seat such that they will rotate and always be aligned with the shaft. Huh, how would that work? I wonder if someone's thought of that before. That's called a self-aligning bearing. Ah, hey, check it out. Why would you ever use these versus these? Some places you want these. Some places you want to have just one. And notice it's about 2 shaft diameters, and it will actually support things reasonably well, whereas the self-aligning one gives you way too much wiggle. But together, 2 self-aligning ones give you all the stiffness you need. Everything has a place. Everything has a niche. Your goal is to identify what is the place and niche for things. Now, this table here calculates for the different types of shaft supports: cantilevered, simply supported, fixed simple, or fixed fixed, which is very difficult to get. How strong the shaft is against buckling. If I push too hard, will it buckle and break? I'm not going to use the pen because I'll hurt myself with that. I have just the thing. No, we're not going to use that one. I don't want to break. Those are too soft. I have, well, I guess we will use this guy. This is a piece of plastic. And when I'm pushing on it, it's very strong, but this, if it's off a little bit, that was a buckling instability of sliding away. Aha, I know how we can cut through this problem. Okay, shaft, pushing on it, oh, that's very nice. Push too hard, doink, bends. That's buckling. I let go, it comes back. That's called elastic buckling. You push too hard on something, and that's not very repeatable. Boink. That's an inelastic buckling, runs away, instability. It's not just for pushing on it with a force. If I was pushing on this with a force and a shaft in compression, and it was spinning, I can also have a rotational buckling where it starts making an awful noise. Because the slightest little bit of non-straightness, as it starts spinning, the center of mass of the shaft is now off from the center of stiffness, and that's when you get a rotational instability. So the world of shafts also includes dynamic analysis. Very, very, very important. Alignment of shafts. Shafts can be misaligned this way. That's vertical parallelism. Shafts can be misaligned that way. That's horizontal parallelism if you're using multiple shafts in your structure. How do you attach stuff to shafts? Well, we went over the use of keyways, the use of shapes. Do not ever, 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 unless you enjoy paying me exorbitant consulting rates so I can fix your problem and then go scuba diving or skiing more, use component. Here's the hub, and here's the set screw. Whether you're using a set screw to push into the shaft and transmit torque through a set screw. So, yeah, but I can buy stuff out of catalogs like this. What do you mean don't do that? Again, if you're designing a cute little machine to do a little demo, that's fine. But a production machine, what happens is this cup here at the end of the set screw, as you have variations in torque, it starts to work its way loose, and you start to wear, and eventually it will boom, spin out. And zzz, the wheel will spin free. The purpose of a set screw should only be to keep a key engaged so it doesn't migrate out. Some of the very, very small components you have in small shafts will sometimes have a set screw that pushes on a flat. And that is a rather lame attempt to try and enable torque transmission because the contact point is here at a much smaller radius than the radius of the shaft. And the idea is that this acts like a wedge. The problem is the mechanical advantage is in the wrong direction. So a little bit of torque creates a huge force level on the set screw to the flat, which then more rapidly creates, earlier I said, this little wear problem. Little wear problem, it generally leads to early failure here and this thing spinning. So the only time you're justified in using a set screw to a shaft for, quote, torque transmission is never. The only time you would use it is if you're not transmitting torque. All you're doing is going along for the ride, like holding an encoder wheel in place. So there is no load on it other than just the inertia of the wheel. You need to have a positive mechanical engagement. Now, one of the opportunities that I've seen that hasn't been taken up on yet, that someone may want to think of one day, is for small motors. Shaft comes out. How do you attach for example, a pulley to the shaft of a very small motor? Well, there's all kinds of very interesting taper lock flanges for big stuff. Or can there be taper lock flanges for little stuff? A taper lock flange being you have taper, another taper, and then the shaft. As this taper is driven in, this segments the taper around, squeezes the shaft and squeezes the pulley and locks it in place. This is used on big, heavy machinery, and you'll see this sometimes for smaller machinery. It takes an extra part. Remember this shape we saw earlier, the trilobe? Why is there not a standard for little motors? Trilobes are often used in many, many types of shafts to have fantastic mechanical engagement. It's like using a socket wrench. Why are these not used on little motors? If I was designing a machine and I used hundreds of thousands of little motors, maybe tens of thousands of little motors, maybe I would just take the little motor and use that motor with a grinding wheel, and I would custom grind little trilobes in all my shafts and then put the mating trilobe feature in the hub of my pulley. So this shape here would be trilobed. And I could broach that in. This is the kind of thinking you have to go through. Shaft, torque, method of transmitting torque, torque, force times radius. How do I get a force, transmit a radius, minimize stress, do not want to cause fretting, wear. This is the menu of thinking you have to go through your head. Okay? Very, very critical. When you're done designing it, basic analysis, yes, use your finite element analysis to focus in and really check those details. Because if you're going to send off a product that you're making hundreds of thousands or millions of, and you don't get this one little pulley right, and it starts to fall off the shaft, the rest of your brilliant, beautiful machine is totally worthless. Every one of them are going to come right back to you. Another way of attaching things to a shaft is by using a press fit. The press fit calculations are very basic, straightforward. They're in the text. There's a nice design spreadsheet, pretty color pictures. And the key to a press fit is when you press one part into another, how much press? If here is a wheel, and I'm going to press fit a shaft into the wheel, what is this amount, this interference delta for the shaft in the hole of the wheel? If it's too big, do I end up failing the material in the wheel and causing problems? If it's too small, I'm not pressing hard enough and I will spin. These are pictures I drew to show the different conditions for when the shaft is too big or too small for the wheel based on when the wheel is spinning, the wheel expands due to centrifugal forces. So you may look just fine the way it is now, but when it starts spinning, it starts, woo, you lose the torque transmission. You may take this wheel that's maybe an aluminum hub on a steel shaft, and everything is fantastic. No problem. Beautiful. You ship this product to the desert. Maybe this is controlling a heliostat for tracking the sun. And it gets really hot, as it happens to in the desert sometimes on sunny days when you want to generate electricity. And there's a wind load, and the heliostat, whoop, doesn't work because the torque was too much for the press fit because the aluminum expanded more than the steel. You want to shrink something on, so it means you want to heat up your aluminum so it expands, place it over the shaft, and then let it cool down. You want to get it off after you've done this. How do you do these things? Do you think ahead to, here's the shaft, and here is the wheel that was pressed on or shrunk on, and now I got to get it off. And if this expands more than that, do I take a torch and heat this? Yeah, sometimes that's done. Have I thought ahead that, well, the shaft could have been hollow, and that really would not affect the stress state at all? So I could just pour liquid nitrogen in here and shrink this, whoop, preferential to this, and it would pop right off. These are the types of questions that you can ask for shrinking or press fitting shaft onto a hub. It's all very predictable, very analyzable. The theory actually works. What doesn't work so well is you'll find sometimes the amount of interference is on the order of a few microns, maybe 10 microns, depending on the size of the system. And hitting your machining tolerances reliably, that's part of your robust quality control, that when I'm designing a production part that uses a press fit, I will run my spreadsheet analysis where the spreadsheet allows me to put in the loads I want, but also the tolerance on the shafting in the hole to make sure that on the high end of tolerance, when the shaft is the small end of the tolerance and the hole is on the large end of tolerance, I still have enough interference fit to transmit the loads I want. And vice versa, if the shaft is on the large end of the tolerance and the small is on the whole end of the tolerance, when I push the shaft in there, I don't actually yield the material and cause it to break, because that's also a bad thing. And these tolerances on press fits are pretty close. You often have to have a precision ground or a reamed or bored hole to make it all fit together exactly as you want. But if you can economically hit those production requirements, and the spreadsheet allows you to actually deterministically to figure out the tolerances you need, a press fit can be a fantastic way, low cost, economical, robust, of achieving the design you want. Next, let's talk about couplings. So the press fit is a way of coupling, or the key is a way of coupling the shaft to the wheel, but it's assuming you have a rigid connection between the two. That's what you're going for. But what about if I want to have some misalignment? So for example, I want to have a shaft, for example, that can push on something but allow for misalignment. This kind of ball joint, for example, used in these hexapods. These shafts here are coupled to the base, and you see how that rotates. That's just, if this was a shaft, where this shaft was driving power to this one, that would be a universal joint. If it's not, this just allows the full degree of freedom I want to when I change the length of this leg. This is a coupling that's coupling this shaft to this structure, or a coupling that would be coupling this shaft to another shaft. If you look under a car or a truck, it's actually easier to see the drive shaft with the universal joint couplings. There's many different kinds of couplings, and again, it boils down to what's the function of the coupling you want to achieve. This type of joint here is simply just a spherical joint, or some people would call it a ball and socket joint. It has 3 degrees of freedom: rotation, and one angle and a second angle, or 3 angular motions. Remember back to topic 4 on linkages. This type of joint here is called a universal joint. And there are several types of universal joints. This one, these are based on across axes. And whether the element in here is a square or here is actually a little ball, either way, it's essentially the center element is a floating element called the spider. And schematically, it would be drawn like this. This is the yoke off to one shaft. And this is the second yoke, which is orthogonal to the first one, goes off to the next shaft. When the shafts are misaligned, as we showed earlier, you can see how these bearings allow shafts to move. Now, an interesting historical study of this. This is sometimes called a Hooke's joint. It was absolutely critical for the creation of the automobile because you can't align the motor transmission exactly to the differential for the drive shaft, differential to drive the wheels by the drive shaft. You've got to allow the car to flex and move and still transmit the torque without wearing things out. In the early part of the automotive industry, these joints were made, and just like in the one I just showed you, sliding contact friction. No problem. Except with a lot of use, they wear out very quickly, so there's a lot of repair. Fast forward to early part of the 20th century, in Torrington, Connecticut, there was the Torrington Needleworks. And remember earlier we talked about going into Lowell, for example, and looking at the textile museums. And vast quantities of needles were used in the weaving industry. Weaving industry moved away. You're running a needle factory and you don't have so much need for your needles anymore. And it's going to shut down and you have no money. And your universal joint in your car has worn out and you don't have the money to fix it. And you're looking at it and you're really upset. And you think, what am I going to do? How am I going to... I'm not going to have a job because they don't need so many needles. My U-joints have worn out. I can't afford to put in... Ooh. Oh. I can stay warm in the winter by rubbing my hands together. Huh. Ah! So the dude at Torrington Needleworks took his universal joint and put in needles, literally needles. So here's the shaft. Needles, lots of little thin diameter, small diameter, thin needles because there's not a lot of space in these joints. Okay. And then here is the cup around it. So the spider on the center, and then these became the needles. They were called needle bearings. Fantastically brilliant, mega profitable invention that enabled the Torrington Bearing Company to be born. Major problem solved for the life and robustness of drive shafts, just by this dude paying attention. Okay? Think about it. Also think about when I have this discrete shape, as this rotates, there's something funny going on. And if you think about it, you work through it nicely, and there's a lot of very straightforward analysis you can do. As I rotate through an angle theta, this angle phi, well, as I go 2 pi radians, or 360 degrees here, it's like conservation of momentum, conservation of energy, just kinematic constraint. This one will also have to move 2 pi. No problem. But the issue is, if I plot theta versus phi, or theta and phi, excuse me, theta comma phi as a function of time, the difference between the two, excuse me. While this one is going constant, zzz, this one's going zzz, zzz, it's speeding up and slowing down. That's a problem. Is it? Well, one, it's going to make some sound. But the real issue is I want constant RPM on my motor to not make my vehicle lurching. So what happens is drive shafts will have one universal joint, two universal joints, and you phase this so the speed up caused by this one is canceled by the slow down caused by that one. And you run them exactly out of phase such that the input and output shafts have exactly the same speed. And the drive shaft in the middle ends up going the same speed, but that kinematics is canceled out by the use of two joints out of phase. What happens if I only have one joint? That's a problem. Why would I only have one joint? Well, maybe I've got a front wheel drive car where I don't have a lot of room. Maybe I want to have my transmission and have right off to the wheel being driven. What would I do then? Well, in the mid-1920s, the guy invented what's called the constant velocity joint. You go look up who that person was. And why did the invention kind of hang out for the next 40 years or so? Well, about 20 years was the next part of the invention, another 20 years later before it became commonplace. And that's the CVT. How can I make a universal joint that has constant velocity? How would I do that? Where would I start as an inventor, as a designer? I kind of got to start with something that's rotationally symmetric through all ranges of motion. How would I now couple torque through this simple spherical joint to make it a spherical universal joint? How would I make a universal joint using a sphere, a true sphere in rolling motion such that I get these motions, but I transmit a torque? So look up CVTs and the history of CVTs. They're fantastically interesting. What about other types of coupling? Servo couplings, for example. Well, servo coupling is a way to take the output torque from a motor and couple it into, for example, a ball screw. How would I take my roller screw here, attach a motor to it, and spin it, and allow for misalignment between the two? Because I just said earlier, you have to be very careful of misalignments. Screw shaft, supported by bearings, motor, shaft. And I don't want to have this spaced far enough apart such that I could use two universal joints. That's no good. How do I couple these in a short space in a machine? But I got to be careful because the function of these bearings is to hold this shaft rigid. But there's bearings in here in the machine that if I just put a rigid coupling between these two, these bearings and these bearings are going to fight each other. Remember St. Vinay. I need something that will transmit torque but allow for some misalignment and not get me too crazy on this nonlinear speed up, speed down effect we just talked about. Well, it turns out that this is one of the most common design challenges, not so much the word because it's done very, very often and handled very, very easily. But it's one of the most common design scenarios you're going to find in designing equipment. And there are a number of different types of couplings that can be used. This, for example, is a spider coupling. And a spider coupling works, typically you'll have 4 teeth. And this actually is a small one, so it's only half a spider. The spider here, if you have 4 teeth on the input, 4 teeth on the output, and the input and output are coupled through this 8-legged, the spider. So that goes together like this. The input teeth. The spider is a polymer, and typically the shape of these teeth, they're slightly crowned on this surface here. So that's when the mate comes in and is pushed in, and I will push it all the way in. This is tight. You see, why is it so tight? How's that a coupling? And then to make it reasonably tight so there won't be any backlash. But then this has, see, it can allow for some misalignment between the shafts. The problem is, although this works, you got to make sure you don't say, well, I got a coupling. I don't need to worry about misalignment. All couplings have finite misalignment capability, and typically the misalignment that they allow causes a load, a radial load on the shaft. That's your parasitic load from the coupling. And that has to be part of your design analysis for rational selection of the tolerancing of the alignment between the shafts, such that ideally you put a coupling in there, but it doesn't do anything. It could be a rigid coupling. You want it such that the misalignment capability offered by the coupling is really just an insurance policy. What about other types of couplings, like tooth couplings? So here we have some 3D printed teeth that you can say, why can't I just engage teeth like this and allow for some misalignment? But see how I'm getting a little bit of backlash? Also notice with a tooth coupling, as I twist, see the way it wants to come apart? Say, well then fine, don't have an angle in the teeth, just make them straight. But then when you have straight teeth, then you will always have backlash. Unless you think of, all right, let's take the straight teeth and let's make them such that one of the teeth, each of the teeth are angled wedges that way, and the receiving end at the root of the teeth are angled the other way, such that when I put it together, you see this backlash? But when I engage, the tooth by the wedge is forced to bend out, and it allows you to now have sideways motion or misalignment of the shafts by the individual elasticity of the teeth, but where the teeth have engaged with those wedges, they're always preloaded. So this is another type of coupling that can be had. This actually came out of the design class that this book was based out of. I don't know if anybody actually makes it, but we published it as in the text, and you can build one. You can build them yourself really easy. No patents. Anybody can make them. They work, taste great, less filling. Then you have flexible couplings, helical couplings, plate-type couplings, chain-type couplings, vast quantities of different kind of couplings, all designed to try and make them as stiff as possible torsionally, because that's the functional requirement, transmit torque, but as compliant as possibly in every degree of freedom other than the torsional mode. And that is a real challenge that is almost solved. Maybe you'll be the one that solves it exactly. The next thing on couplings, remember this, not just for torsional coupling. Here, for example, is the shape of a lead screw, or a ball screw, or any kind of a screw. And here is the shape of a linear bearing carriage, the rails for it. And you say, they're not curved, they're supposed to be straight. Yeah, but remember, nothing is ever perfect. How do you make it such that you can have the nut coupled to the linear motion carriage such that as the screw turns and the nut invariably wibbles about, you can couple it to your linear motion carriage to move and not cause so much bouncing? Remember, in fundamentals, the concept of the center of stiffness and where do you want to mount the coupling is often as important as the coupling itself. So make sure you go back to topic 3 and look up center of stiffness and where things need to mount to cause minimal tilt, because if you have tilt, now you have angular errors amplified by distance, or the whole concept of an Abbe offset. If you give a mouse a cookie, he'll want a glass of milk, et cetera, et cetera, et cetera. Design your machine to minimize the need of analysis and problem solving in the first place. You'll have plenty of opportunity for solving problems. No need to make extra ones. Now, if you look at shade tree engineering, so to speak, and making things fast and easy. A pin-type coupling, pin in a slot, can be made to act like a universal joint. It can also be made, because the pin in the slot, to accommodate axial motion. And then now you have to worry about, as the pin goes through the slot, what is the surface or the contact stress between the round pin and the edge of the slot, given the torque that's being transmitted. Okay? But you should never be afraid of, if you're in a short use, for example, one of these design contests, and you need to pack something in a small space, designing your own coupling. Just look at the motions that you need to require, follow the flow of forces. You have the tools now to think about them, calculate contact stresses between the pins and the slots. That's actually coming up in topic 9, but I'm sure you've jumped ahead and read it already. Do not be afraid of designing your own couplings. It's very straightforward. Just don't forget the details.